So the concepts I needed to explain were how resting potential and action potential work. First of all, it's important to understand that both resting potential and action potential are part of what is called the membrane potential. As we've learned in class, potential is a separation of charge and therefore an ability to do work. If we were to look at the cross-section of a neuron at rest, we would notice that there are more positive charges outside the membrane than inside the membrane. This is called an electrical gradient. As such, membrane potential can be described as a difference in total charge inside and outside the cell. Resting potential in a neuron means the difference of charge inside versus outside the cell when a neuron is not firing any signal. As we can see in this image, the average voltage difference of a neuron which is at rest is approximately minus 70 millivolts. In other words, the inner part of the cell is roughly 70 millivolts less positive than the outside. As such, this resting potential could eventually lead to an action potential if the stimulation outside of the cell is big enough to bring the membrane's potential from minus 70 millivolts up to minus 55 millivolts. This minus 55 millivolts is what is called the threshold. Furthermore, it's important to note that neuron cells are what we call excitable cells. In a neuron, action potential is a rapidly propagated electrical impulse that allows for long-distance signaling in the nervous system. It is described by a cycle of membrane depolarization, repolarization, hyperpolarization, and then return to rest. When the voltage approaches minus 55 millivolts, the sodium voltage gated channels that are on the membrane of the neuron will open up very wide. This allows for a huge amount of sodium to rush inside the cell, which creates this depolarization. And consequently, the voltage increases very rapidly. When the voltage reaches around 30 millivolts, the sodium-gated channels become inactivated, and then the potassium-gated channels come into play and open up very wide. This allows potassium to leave the inside of the cell and go outside of the cell, which drops the voltage back down to around minus 70 millivolts. Furthermore, it's important to understand that action potential travels down an axon. This is because the first depolarization or action potential that occurs near the axon hillock creates a positive feedback loop of depolarizations to the segments next to it. This means that if we were to insert microelectrodes in an axon during an action potential cycle, the measured value would be greater or equal to minus 55 millivolts, depending on when we measure the voltage. Also, as we've seen in class, in an electric field, the electric field lines point from the positive charge or the positively charged area to the negative charge or the negatively charged area. As such, the electric field lines of the membrane of a neuron would point from the outside of the membrane towards the inside of the membrane, since the outer part of the membrane has a more positive charge and the inside part of the membrane has a more negative charge. Furthermore, from a physics point of view, or from what is called the cable theory, axons can be described as cylinders composed of sections with resistance and capacitance. As seen in class, capacitance is an ability to store electrical energy, and a capacitor is basically composed of two conducting plates with an insulator that is separating them. As such, membranes of neurons act as great capacitors, since the inside and the outside of the cell let charges flow very freely, since they are water-soluble parts, and since the lipid bilayer that separates the inside and the outside of the cell is very resistant to the flow of charge and therefore acts as a great insulator. In the end, the action potential of a neuron is part of what is called the all or none principle, which basically means that an action potential will only occur in a neuron if it hits a certain threshold, which in this case is minus 55 millivolts.